The following video is on areas. We'd like to try to find the area under the curve y equals x squared from x equals 0 to x equals 2. In other words, this red shaded region. If we wanted to approximate this area, we can note that it looks sort of like a triangle. So we could draw the triangle connecting the two endpoints of the interval. And we know how to find the area of such a triangle. The area is going to be 1/2 base times height, and so we end up with an area of 4. However, we can see that this is actually a lot bigger than the actual area of the red shaded region. So in this video, we're going to try to come up with better ways to approximate the area of a region under a curve. So how can we get a better approximation? One way to do it is to try rectangles instead of triangles. So what I'm going to do is I'm going to start by splitting the interval from 0 to 2 up into 4 equal-sized regions. So just looking at the x-axis, I've marked off in purple 4 equal-sized intervals. And now what I'm going to do is take the right end point of each interval, trace it up until I hit the curve, and call that the height of the rectangle. So far I've drawn the first rectangle, here's the second rectangle, the third, and the fourth, and each time the base of the rectangles is the same. In this case they're all 1/2, and the height was found by using the right endpoint. Now we can just find the area of each of these 4 rectangles by finding the base and the height. So the height of rectangle 1, we know that we went over 1/2 units, and we plugged that into the function. So that's going to be f of 1/2, which in this case, the function was x squared, so that's going to be 1/2 squared, or 1/4. That means that the area of the rectangle is going to be the base, which is 1/2, times the height, which is 1/4, so we end up with 1/8. We can repeat the process for rectangle 2. Notice for rectangle 2, we had to move over 1/2 units twice, which means that we've been plugging in x equals 1 to get the height of the function. So that's going to be f of 1, which is 1 squared, or 1. So the area of rectangle 2 is going to be the base times the height, which is 1/2. The height of rectangle 3 is f of 3/2, because for this one, the base, we had to move over 3 times from 0. So we had to move over 1/2 plus 1/2 plus 1/2, which is 3/2, and plug that into our function to get the y value. This ends up giving us 3/2 squared, which is 9/4. So the area of rectangle 3 is going to be the base times the height, which is 9/8. And finally, we do the same thing for rectangle 4. Notice that this time we've had to move over 1/2 4 times, which is the same as moving over to 2. So we have f of 2 equals 2 squared, which is 4. And the area of the rectangle is going to be 1/2 times the height. So that's 2. So now we've found the 4 areas of these rectangles, we can add them all up to get the approximate area under the curve. So we end up with 1/8 plus 1/2 plus 9/8 plus 2, which ends up being 30/8, which comes out to 3.75. Notice that we ended up with something that was slightly smaller than our previous answer, which was 4. This is slightly smaller, so we've actually gotten a better approximation using this method than we did when we used triangles. Let's try another example where we have more rectangles. So this time I've split the interval into 6 equal-sized chunks, and just like before, I draw the rectangles by choosing the right end point of each of my 6 intervals, tracing it up until I hit the curve, and calling that the height of that rectangle. So now the base of the ith rectangle, remember that we've got a total length of 2, right? From x equals 0 to x equals 2, the length there is 2. And I've split that whole interval into 6 equal-sized chunks. So that means that each chunk has length 2 over 6, which is the same as 1/3. The right endpoint of the ith rectangle, so here I've numbered the rectangles, and for the first rectangle I would only have to move over once, which would be 1/3. For the second rectangle I would have to move over 1/3 again, which would give me 2/3. For the third rectangle I would have to move over one more time, which would give me 3/3. So the right endpoint is going to be 0 plus I times 1/3, which is I/3. The height of the ith rectangle is just going to be f of whatever that right endpoint is, so f of I over 3. Remember the function here is x squared, so I'm going to do I over 3 quantity squared, which is I squared over 9. Finally, the area of the ith rectangle is going to be the base times the height, so that's 1/3 times I squared over 9, which is I squared over 27. Now if I want to find the sum of all the areas, or the total area, I add up each of the rectangle's areas as I goes from 1 to 6. Remember, I is counting the rectangles. So the sum as I goes from 1 to 6 of I squared over 27. I can pull the 1 over 27 out because it doesn't have an I in it, and I'm left with 1 over 27 times the sum as I goes from 1 to 6 of I squared. Now we use our formula for I squared, which is n times n plus 1 times 2n plus 1 over 6, and in this case n is 6. We simplify and we end up with this going to 91 over 27, which is 3.370370 dot dot dot. Notice that once again we've gotten a value that's slightly less than our previous value. It's still going to be slightly bigger than the actual area, but we are getting closer to the actual area under the curve. I can also do this in general. So here I've split my interval up into an unknown number of equal sized chunks. And I can draw the rectangles using the right-hand endpoint to determine the height. So the base of the ith rectangle is going to be the length of the total interval, which is 2, divided by the number of rectangles, which we said was n. The right endpoint of the ith interval, each time I move over 2 over n units to find the right endpoint. And so if I'm finding it for the ith interval, I'm going to have to do that I times. The height of the ith rectangle then is f of this number, which is 2I over n. And remember, our function just squares things, so we get 2I over n quantity squared, which comes out to 4I squared over n squared. So finally, the area of the ith rectangle is going to be 2 over n times 4I squared over n squared, so the base times the height. This comes out to 8I squared over n cubed. So the total area of all of the rectangles is the sum as I goes from 1 to n, remember I counts the number of rectangles, of the area of the ith rectangle, 8I squared over n cubed. We can pull the 8 over n cubed out because they don't have any i's in them, and we're left with 8 over n cubed times the sum as I goes from 1 to n of I squared. Once again, we use the formula for I squared when the sum goes from 1 to n. And we're left with 8 over n cubed times n plus 1 times 2n plus 1 over 6. We can see that as n gets larger, the areas of the rectangles will get closer and closer to the actual area under the curve. So, to get the most precise answer, we want to take the number of rectangles going to infinity. Notice that what I've done here is I've taken the limit as n goes to infinity of the area that we found on the previous slide, which was the area if we had n rectangles. If we try direct substitution, we get infinity over infinity, which is one of our indeterminate forms. So I'm going to end up using our sneaky trick from earlier. If I distribute everything out on the top and the bottom, I'm going to have 16n cubed plus a lot of other stuff that I know I'm not going to care about over 6n cubed. Since this is going to be the highest power of n in the top and the bottom, and since they both have the same degree, we know that the answer will be the leading coefficients. So I'm going to have 16 over 6, which comes out to 8 over 3, or 2.66666666. This is the actual exact area under the curve, y equals x squared, from x equals 0 to x equals 2.